Hello, everyone, and welcome to our live stream for our online classes. My name is Matthew. I am one of the teaching instructors, teaching assistants for the online classes, but you may have found us through other means. Welcome to the stream. This is the first one for 2024. We are happy to have you here, and we are looking forward to your questions. So the way this works is we have people post live questions in the chat, or send them through email. If you scroll to the top of the chat, you can see the email address where you can send those. Please make sure you subscribe to our channel or like the channel, and then hit that bell icon so you find out about upcoming live sessions. Chris, I'm going to hand this over to you to welcome everyone, and then we will get started with questions.
Okay, welcome everyone to a new year, and it's actually 10 years we've been doing online classes now in MOOCs, which is quite a long time, right from the beginning of the phenomenon. So if you found us through our classes, welcome, or just happened upon this channel and this means of asking questions, welcome, and the floor is open for questions on astronomy.
Excellent. The first question is from Faisal. Whenever the Earth slows down in its rotation around its axis at a rate of fractions of a second per year, does this mean that the Earth was faster in its rotation around its axis in the past? And if so, how much faster?
Yes, it does. So it's an interesting phenomenon, very slow lengthening of the day. And if you project that back, extrapolating backwards is a little tricky because we just don't have direct geological or astronomical evidence for the length of the day in the distant past. But the projection would be that when the Earth, soon after the Earth formed, or within the first billion years, the day's length was probably about 18 hours. So it's been extended by a third in that period of time. So it's a very slow, very gradual thing. And it's essentially caused by the tidal interaction between the Earth and the Moon. So the two bodies are coupled by gravity, and they're also coupled in terms of angular momentum, or the spin vector of both the Moon and the Earth, and that's what leads to this very slow lengthening of the day.
Excellent. Thank you very much. The next question is also from one of our live participants who would like to know, Adrian Murray asks, what would it take to be able to see outside of the known universe?
Well, the known universe is by definition what we can observe because it's based on empirical data. And in fact, there's a fundamental limitation that means we can't really see outside the known or the observable universe, because the limitation is imposed by the finite age of the universe and the finite light speed travel. So those two things are finite, and that means there's a limit to the distance we can see out in space since the Big Bang. That light just cannot have reached us from more distant regions, and that makes a fundamental limitation, and means actually we cannot, as a matter of principle, we can't look outside that known universe.
Excellent, thank you. The next question is from Jim, who would like to know, the question is, explain the James Webb new discoveries. So maybe in general you could talk about some of the most major finds from the James Webb Space Telescope up to this point.
Well, probably the biggest discovery, which is based on multiple observations, so it's not a single study, it's a number of groups working on the same issue, is the formation of the first large galaxies and black holes in the universe. This was really partly what Webb was designed for, first light, measuring the first light in the universe, first stars and galaxies. And it's made significant progress, and the surprise behind these observations is that there are extremely large, well-formed, mature galaxies and fairly large black holes, like a fraction of a billion solar masses, within the first half billion years of the universe after the Big Bang. That's really early, and modern theories of galaxy formation and black hole growth don't easily accommodate that rapid growth of a galaxy in its black hole. So I say that's the single most surprising result from James Webb, coming from a number of groups and not just a single observation.
The next question is from Jerry Greer, who's on with us live. Do we have proof of metallic hydrogen inside of the gas giants, especially Jupiter?
No, we have inference of metallic hydrogen. First of all, metallic hydrogen is a very bizarre state of hydrogen. Hydrogen, of course, on Earth and in terrestrial environment is a gas, it's a very light gas. It's certainly possible to liquefy it under extreme pressure, so we have liquid hydrogen, and that's a routine technology. But that's a modest amount of pressure, maybe hundreds of atmospheres. If you get up to thousands of atmospheres of pressure, which is what you would experience at the base of the Jovian or gas giant atmosphere, then hydrogen gets compressed into almost a quasi-solid, quasi-liquid state called metallic hydrogen. And metallic, therefore, implies that it conducts electricity, which means that in this state, the single electron attached to the protons in the hydrogen is moving freely and therefore could potentially carry current. This is a very extreme state of matter, and we cannot duplicate it in the lab.
Excellent, thank you. The next question is from one of our live participants who would like to know, Cam Vivek sent an email. The universe is accelerating, kind of like how things accelerate down to the surface of the Earth when you drop something like a ball. Is it possible that the universe is accelerating because there is something larger outside our universe and is pulling on everything inside our universe?
I mean, that's an interesting conjecture, and in principle, it could be possible that if the universe is essentially a very good vacuum, but if for somehow the universe were within a larger volume where the vacuum was even greater or even closer to pure vacuum, possibly that creates negative pressure that leads our universe to expand faster. But in fact, that mechanism doesn't really work because our universe is almost a perfect vacuum, so it's hard to imagine an external state that would make it accelerate. Rather, it seems that the accelerating universe is a property of space-time itself. That dark energy, which is the phrase we use to describe the entity that's causing the accelerating expansion, is a property of space-time. And so as the space-time expands, it makes more space-time with negative pressure, and that process accentuates and accelerates, and that's what leads to the accelerating expansion.
The next question from one of our live participants is from Parth Agarwal, who asks, how are quasars formed?
Quasars are active galactic nuclei. They're extremely massive black holes at the center of otherwise normal galaxies, where the accretion of material in the environment of the quasar creates enormous pressure, particle acceleration, and electromagnetic radiation across the spectrum, often from radio waves to gamma rays. These are extreme objects that were first understood and discovered in the early 60s. So what makes a quasar is a collapse of a black hole, so a formation of a massive galaxy where a seed black hole grows very quickly to the level of hundreds of millions or billions of times the mass of the sun. And at that mass, it can accrete material, and while the black hole remains black, the environment of the black hole is an intense accelerating radiation zone, creating enormous amounts of energy. In a quasar core, the area around the black hole outshines the parent galaxy, sometimes by factors of hundreds or thousands. You're muted.
Thank you very much. I'm sorry. The next question is related to one of our earlier questions, related to the Earth's rotation slowing down. They'd like to know, so we talked about the day being shorter in the past and the moon being closer to Earth. So can you talk a little bit about how the moon's distance and the Earth's rotation speed kind of relate to each other and what happens as they slow down?
Right. So the gradual slowing down of the Earth's rotation is a transfer of angular momentum, and that's what, in the sense, that's in the end what makes the moon move further away. And the amount by which the moon recedes from the Earth is a few centimeters, maybe 4 centimeters a year. It's a tiny amount, but it's measurable and it's understandable. So the mechanism and the relationship is simple physics. It's conservation of energy and conservation of angular momentum applied to two rotating, gravitating bodies, the Earth and the moon.
The next question is from one of our live participants, what would it take to make Mars' atmosphere thicker with an oxygen atmosphere?
So the idea of making Mars potentially habitable, which is what that question implies, is sometimes called terraforming Mars. It's not impossible, but it's an extraordinarily difficult, expensive, and time-consuming undertaking if you ever did it. Remember, Mars' atmosphere currently is about 1% of the pressure of the air we breathe, and it's made almost entirely of carbon dioxide. There's no oxygen at all. So to make an oxygenated atmosphere, you would also have to thicken the atmosphere up, and you'd have to have a way of generating the oxygen naturally. And the best way to do it, of course, is using microbes with metabolisms that release oxygen, which is how the oxygen of the Earth got here. So we'll just be replicating what happened on the Earth a long time ago. But that took a long time, so it's an indication that this could not happen quickly. So to generate the microbes that could oxygenate the Martian atmosphere and thicken it up, you first have to get a habitable surface, and so it's too cold. So the first thing you do is you have to heat the planet, and so there are mechanisms of adding energy to Mars where you can get more carbon dioxide in the atmosphere. It's frozen underground, and you can release it from the rocks, and then you'll gradually create a greenhouse effect. So you essentially want to create a runaway greenhouse effect on Mars to raise the temperature. And that would take what is subsurface ice now and turn it into water. And in that water you could grow microbes that could generate oxygen, and that oxygen would gradually work its way into the atmosphere. So you can see just by that description that it's a complicated, convoluted, time-consuming, and a very difficult process to exercise on a planetary scale. It's not impossible, but nobody really has a realistic plan for doing it because the cost would essentially be enormous.
Excellent, thank you. The next question is from David Gold. What opportunities does quantum computing provide for the astronomy field? Are there any quantum computing projects being piloted today in astronomy?
So astronomers are often pushing the envelope of computing as users, however. Astronomers typically don't design computers or the circuits that are now involved in quantum computing as it moves out of the lab into the real world. So that's going to be the case in the future. Astronomers will be power users of quantum computing as it emerges, as they are power users of supercomputers, conventional ones right now. But astronomers are not involved in doing this research. This work happens in labs and in physics labs, essentially. And quantum computing is not ready for prime time yet. It's not able to do the kind of calculations that astronomers need. So I would say in the evolution of quantum computing out of the lab into hands of researchers, we're probably 20 years, maybe 15 or 20 years away from that really happening. Quantum computing is progressing every year. There's new landmarks and new numbers of qubits or quantum bits kept under super cold conditions able to do calculations, but the number still is very modest.
Excellent, thank you. The next question is from an email. Wendy Traver asks, she says, Happy New Year to all. More than one Higgs boson has been theorized. What function could these other Higgs bosons serve?
The theory of particle physics is evolving. There's a disappointment in a sense that since the discovery of the Higgs, which is a decade ago now, over a decade ago, there have been no fundamental discoveries in the field. The Higgs boson is the entity and the force, the sort of force out of the vacuum of space that gives mass to fundamental particles. And so there are theories that predict that the Higgs is not unique. The trouble is these are just theories and none of the phenomenology has indicated any other massive particles. And so one of the big disappointments of the Large Hadron Collider in the last few years has been the absence of any signatures of other Higgs-like particles at higher energies. Essentially, it's not there. I mean, every now and then there's a little news story, but it sort of goes away. So I would say at the moment, all the theorizing doesn't have any experimental support.
The next question is from Adrian Murray, who's on with us live. The Earth slows down a bit every time a spacecraft slingshots out of Earth's orbit. Could this eventually affect the Earth's rotation noticeably?
So in principle, yes. The slingshot mechanism is a transfer of energy and angular momentum. And so when you speed up a spacecraft, you are slowing down the planet. But if you do the math, you can answer the question fairly easily, because the amount of slowing down of the Earth's rotation speed is essentially proportional to the ratio of the mass of the spacecraft to the mass of the Earth. And the mass of any spacecraft compared to the mass of the Earth is a tiny, tiny, tiny number, a trillionth or far less. I can't do the math in my head, but it's an enormously large fraction. So it's an enormously small fractional change in spin rate. It's undetectable, and there's no prospect that we could detect it.
The next question is from Horst Melcher, who asks, Earth's velocity from daily rotation to move around the sun to the motion of our galaxy around the rest of the universe, how do astronomers measure velocity due to the fact that there are all of these interacting motions that sort of, pile up on each other?
Right. So the reference frame of velocity and motion is an important subject in cosmology. And so we know about various motions, and we can take them on different scales. We've measured for hundreds of years, actually, the rotation of the Earth around the sun, and we've measured for over 100 years the rotation of gradual orbit of the sun around the galaxy. The Milky Way's motion relative to other galaxies has been measured for 70 or 80 years. So these are old observations. And then on larger and larger scales, we can see clusters of galaxies. So the Milky Way and Andromeda, which are moving towards each other, are both falling into the Virgo cluster, large concentration of galaxies about 60 million light years away. And then there's a larger supercluster beyond that. And all those scales of motion have been seen. And in the end, of course, the universe can't be moving because it's the whole thing. And when people look at the velocities on large enough scales, they find frames of reference which are at rest with respect to the microwave background, which defines motion for the entire universe, or defines zero velocity.
The next question is from Umber Ashraf, who asks, Titan is a moon of Saturn. Can you talk about the possibility of life there?
It's a matter of intense speculation ever since we knew that Titan had bodies of liquid on it, which is it's unique in the solar system outside the Earth in terms of having liquid on the surface under a dense nitrogen atmosphere. Liquid is very cold because it's far from the sun, and it's ethane, methane lakes with a little water and ammonia mixed in. So those are the raw materials, and there will be carbon-rich material, of course. There's cryovolcanism, so there's energy sources under these lakes from the interior of the moon. Is that all enough to create some form of life? Essentially, nobody knows. It's very difficult to make a lab simulation of Titan conditions, so I don't think lab work has been able to shine a light on the problem. People have made some theoretical calculations. It's not clear that with those chemical ingredients you could ever create a replicating molecule like RNA or DNA, and it's not clear you could ever make a cell. But simply we don't know, because this is going to be a very alien form of life if it is. And I think the verdict is unproven, it's unknown, which is why everyone's waiting with keen anticipation for the Dragonfly mission of NASA, which has been recently delayed, which will sample these lakes and look for more direct evidence of possible life.
Excellent. Thank you very much. The next question is from one of our live participants. Mustafa asks, hi, Professor, can you please explain stellar aberration and what that is?
Stellar aberration is due to the fact that the Earth is moving and the stars are seen. So if you think about starlight as it approaches the Earth, it approaches at the speed of light, of course. But the Earth is rotating, and so there's a little vector attached to that from the Earth's motion, which is a small fraction of the speed of light. But that extra vector into a triangle constitutes a small angular shift. So there's a slight aberration of the starlight as it reaches the Earth's surface. That aberration is very small, but it was first measured over 100 years ago. And so it's direct evidence of two things, actually, that the Earth is truly moving through space and that the stars are extremely distant.
The next question is from John in Juneau, Alaska, who would like to know about rocky planets. Can you talk about two things? The first question, we'll just start there, is what factors limit the size of rocky planets?
We don't actually know what the theoretical limits on the size of rocky planets are. We do know in the study of exoplanets that there are many rocky or terrestrial planets that have been found. And in fact, the largest single category of exoplanets is super-Earths. So these are planets that are 5 to 8 times the Earth's mass. However, we also know that the gas giants and the ice giants, Uranus, Neptune, Jupiter, Saturn, and their analogs beyond the solar system have rocky cores. Those rocky cores are not measured very well or directly for exoplanets, but we know what they are in the solar system. So there are cores for those giants that are 5 to 10 times the mass of the Earth. It's an uncertain number. And that provides a sort of practical upper bound in terms of actual measurements for the size of rocky planet, something like 10 times the size of the Earth. It's not clear if certain conditions arise that the rocky planet might grow larger than that, but we've not seen any rocky core or terrestrial planet larger than about 10 times the mass of the Earth.
Right. So the next question was, what's the largest rocky planet that's ever been found?
So the largest rocky planet, we can't really call the cores of the gas giants rocky planets because they're gas giants that have rocky cores, and those cores are not very well measured. If we're talking about just rocky planets, terrestrial type planets, then the largest mass is similar to 8 to 10 times the mass of the Earth.
Excellent. Thank you very much. The next question is from Peter Bafus, who sent an email. Michio Kaku has talked about the latest findings of the Webb telescope, suggesting some galaxies could be older than the universe, with stars forming much earlier than the assumed starting point 13.8 billion years ago. Do these findings somehow undermine the robustness of the Big Bang theory?
I think, as reported by Michio Kaku, I don't know that article or whether it may have been his podcast, I think that's sort of overstating the case. So there's no direct evidence against the Big Bang from the James Webb observations. And that's partly because the estimates of age of distant object is quite uncertain. It's not easy to take a galaxy, say at a redshift of 10, which you can say in the Big Bang model is 600 or 700 million years after the Big Bang, and then show that the age of the stars in that distant galaxy is older than 600 or 700 million years, ergo a problem for the Big Bang. It doesn't work like that. The age estimates for the stars in these distant galaxies are quite uncertain. And that leaves just enough wiggle room that I don't think it's very premature to say that these observations are Big Bang killers.
The next question is from Gregory, who's on with us live. Do Enceladus and Europa have the potential to harbor life? And if so, what would be the key ingredients necessary for such an environment?
Certainly Enceladus and Europa are potentially habitable by microbial life. They both have bodies of liquid water. Enceladus has subsurface oceans that lead to the geysers and the icy jets that we see, that Cassini measured for the first time years ago. And Europa is a water world with an ice pack overlying on the entire moon a sea that could be 5, 10, 20 kilometers deep. We don't really know very well. So both objects have liquid water, protected because they're in distant cold parts of the solar system. They have carbon-rich material, and there are local energy sources from interior heating or from tidal heating by the planet they orbit. So yes, both of those are potentially habitable situations. And to go beyond saying they're potentially habitable, we'd have to know a lot more about each of them. And of course, they're very distant. It takes a mission, a decade or more to plan and execute. And there are plans to learn more about both objects, but I don't think we're going to learn much more in the next 5 to 6 years.
The next question is from one of our live participants. Jerry asks, how much of the sun's mass would have to be ejected for the Earth to leave its orbit?
It would be a large amount. When the sun turns into a red giant, its outer envelope will expand. It's cool as a red giant, but of course it's much hotter than the Earth itself, and so it'll ablate the Earth's atmosphere, but it will not dislodge the Earth from its orbit. There will be some energy transfer, so it will shift the Earth's orbit some. Now at the very end of the sun's life, when it turns into a white dwarf, it can have lost about a third of its mass. And that amount of mass, again, is not enough to eject the Earth fully from its orbit, because the material that comes out is very diffuse, so the energy and momentum transfer is quite small. But it will shift the Earth in its orbit.
Excellent. The next question is from one of our live participants who asks, T. Bollock asks, do you think sometimes we are seeing things that we weren't meant to in the stars?
Not quite sure what that question means. I think we see what we can see with our telescopes. There's no sense that information is concealed from us. It's a question of what we can and are able to observe and what we choose to observe. So astronomers have so many potential targets that they have to use their judgment to decide what is worth observing or looking at, and that means many interesting objects never get studied.
Aditya asks, Beetle Juice, the star, has been unstable recently, as observed by us. Is there any recent information as to what's going on with that star?
Nothing particularly recent, and it's not a surprise. Betelgeuse is an advanced stage of life as a massive star, and as the energy sources change, the star reconfigures and becomes unstable. So, in any situation where the hydrostatic equilibrium, the normal balance between gravity and pressure that keeps the sun, for example, the same size and the same luminosity, more or less, for hundreds of millions of years, that balance is broken in a star as evolved as Betelgeuse. And so that instability is what leads to variations in the light output. So it's completely expected by stellar evolution theory. The variations are some unpredictable enough that there's no exact description of how those variations should occur. And so I don't think we've learned anything from Betelgeuse that has affected our models of stellar evolution yet.
The next question is from one of our live participants. From Einstein's theory, we find that something faster than light is undefined, but at the same time, we saw from Newton's gravitational theory that the gravitational attraction of photons was also undefined. But now we know that that's possible. So do you think that in the future we might find that faster than light travel is also possible with a theory beyond Einstein?
The idea of faster than light travel is not completely ruled out by physical theory. Newton's theory of gravity and electromagnetic radiation was not prescriptive about the speed of light or it as an absolute limit. That didn't happen until Maxwell's theory in the late 19th century, and Maxwell's equations, which yield the speed of light as a universal constant. General relativity does comment on the speed of light because it's a fundamental constant that's part of the theory. But again, there's nothing in the theory of general relativity which relates mass and energy in a volume of space to its curvature that alludes to the speed of light. So it would require some external physics theory, some new type of physics theory, not general relativity and not Newtonian gravity, to accommodate faster than light travel. And no theory has emerged that's been tested and shown to be correct.
The next question is from one of our live participants. Dulneth would like to know if you can just talk a little bit about black holes. What are they, and what do we currently know about them?
Well, we know quite a lot. I mean, black holes have been part of the landscape of astronomy for quite a while. They're predicted out of general relativity, and the first theoretical calculations that suggested they would exist happened in the 1930s and 1940s. The first proof that a black hole existed, a collapsed stellar remnant, was in the late 1960s, Cygnus X1. And since then we've learned about many stellar mass black holes and many massive black holes in the center of galaxies. So there's a good half century or more of research on black holes that essentially tells us a lot about their properties. And I would say with the LIGO detections that started in 2016, gravitational waves, from merging black holes, any shred of a doubt that black holes exist as physical objects in the universe described by general relativity has gone. So the gravitational waves are, convincing proof of the reality of black holes in our universe.
Excellent. Thank you very much. Let's see. So Arif would like to know, can you talk a little bit about why you think that ancient astronomers or ancient astronomical evidence was able to capture or view a supernova, but couldn't figure out that the Earth is moving around the sun?
Yes, the first proper observations of a supernova in the pre-telescopic era, but not by long before that, were by Tycho Brahe. So in his life, 2 supernovae in our galaxy happened. It's kind of unusual because it hasn't happened since for 400 years. And Tycho Brahe used the observations of a supernova and his measurements of planets and stars to prove that the supernova was a distant object outside the solar system, as known at the time. So those are the observations from 400 years ago that allude to supernovae and understanding them. But that was not a physical understanding of supernovae. That did not happen until the 20th century, until we had a theory of stellar evolution.
The next question is...
You muted again.
I'm sorry about that. I missed the button. Ravi sent an email asking, I am curious about data releases from survey missions like Euclid, Gaia, and others. For example, Euclid says that its first data release will be in about 2 years. Is this when science teams will be okay to submit papers for publication and talk to the press, or is this when they will first get their access to the data?
No, the science teams get their data right away, and they get to work on the data right away, and they can publish it. The release schedule really relates to when everyone else can get access to the data. The rules for accessing data from these telescopes and observatories are different depending on the agency. NASA has a general policy of data release a year after the observations are taken, so the science team gets a year exclusively to work with the data. Euclid is the European Space Agency, and their rules are slightly different. So most of these missions protect the interest of the science teams that often built the instruments and created the facility to give them privileged access. But all of these missions, since they're funded by a taxpayer, European or American, eventually make the data public, and that means not just to other scientists, but to the general public if they wanted to look at it.
Thank you. The next question is from one of our live participants who asks, what type of information does Voyager 1, or do the Voyager spacecraft that are way on the edge of our solar system, what kind of information are they sending back to us?
It's amazing that the Voyagers are sending any information back, because they were launched in the 70s, so we're talking about almost half a century of travel through and beyond the solar system. The 2 Voyagers are 2 of 5 spacecraft that have formally left the solar system past the orbit of the outermost planets. The other 2 are the twin Pioneer spacecrafts and the New Horizons spacecraft, which is more recent but was moving much faster. So the Voyagers have entered an area which is formally called the heliopause, and that's a place beyond the solar system where the solar wind meets the interstellar medium, and you actually have a transition in the sort of the diffuse plasma of interplanetary space, and that transition zone has been measured by the Voyagers. So it's very exciting. They of course are extremely feeble. Their remaining battery power eking out at a level of, I think, of just a few watts, but still detectable at a distance of tens of billions of miles, which is amazing. It's not clear when they will finally stop transmitting information to the Earth, but it's been an awfully good long run for both of those spacecrafts.
The next question is from an email. Jean-Pierre asks, when the universe was a finite size at the time of the Big Bang, how is it that it could now be infinite in size when it has been expanding in the meantime? Can you talk a little bit about how it goes from, a finite size at the beginning to now infinite?
Well, the infinite size of the universe is a projection of what might be space-time beyond the horizon. So you can calculate and run backwards the observable universe, the distance to the horizon, which is the furthest we can see in space, going back in time, and then you can say what the size of the universe was close to the Big Bang. And so there's a size versus time calculation that comes straight out of the cosmology. But that size relates to the distance you can see, where information can reach the observer, given the age of the universe that's finite. It doesn't really allude to anything beyond that. So the idea of infinite space, or space beyond the horizon that we can see within the Big Bang model, is an extrapolation and a speculation, because we can't measure that space. And it's not intrinsically part of the Big Bang model that the Big Bang expanding entity is embedded in infinite space. That's an extra hypothesis that you don't have to make.
Excellent. I think your microphone may have gotten bumped a little bit. If you could just kind of double check it.
Okay.
Just got a little quiet there for a second.
Yeah.
The next question is from Zeb, who says, do you think that astronomy knowledge that is known so far is cumulative and being learned in a linear way, or do you think that we learn and forget and then rediscover things? How often does our astronomical knowledge progress linearly, and how much do we sort of backslide and then rediscover things?
That's an interesting question. So I'd say in the long history of astronomy, which is the oldest science, going back thousands of years, there were definitely examples where things were learned and then forgotten. For example, there were arguments made in the time of the ancient Greeks for a heliocentric universe, that the Earth was not the center of the universe. And those arguments were essentially overridden by the stronger personality and arguments of Aristotle, and that whole idea of a heliocentric universe was forgotten for 1.5 millennia. So that's a pretty dramatic example of forgetting something that was correct, and then going back to a wrong idea. It's a little rare to find that in the more recent history, but there are still a few examples. So I would say in the last century, in this century, astronomy tends to move fairly linearly forward, but at a very uneven pace. There are subjects where very little progress has been made. So exoplanets, enormous progress has been made since the mid-1990s, when the first discovery was made. Dark energy was also discovered in the mid-1990s, and we've learned very little since then. So those are two examples of very uneven progress on two fundamental aspects of the universe.
Faisal would like to know, why does dark matter in the universe not gather into a single mass, since it has strong gravity and controls galaxies, instead of being more sort of distributed through the universe?
The reason dark matter doesn't just all aggregate all together in one place strongly is because the universe is expanding. So yes, dark matter has concentrated over time by gravity, but that concentration or collapse of dark matter in the centers of galaxies or clusters or wherever it might be is countermanded by the expanding universe, which is making matter more diffuse. And so the formation of structure and even the formation of galaxies themselves was a sort of battle between the gravity of dark matter forming halos within which stars might form, and the expanding universe, which was tending to make the dark matter spread out and be so thinly distributed that no galaxies could form. So it's been that continual trade-off that leads to the structure we see.
The next question is from one of our live participants. Do you think that we could stabilize a black hole on Earth? So it sounds like, create a black hole on Earth and keep it stable, or perhaps find a black hole and keep it stable on Earth.
So there's no indication that there are any black holes on the Earth. They would have to be small, of course, to not be obvious, and they would, by Hawking's theory, they would evaporate quickly, so they really couldn't survive. So it's pretty unlikely that black holes exist in the terrestrial environment. As for creating a black hole, in principle it's possible, because we know the density of matter you would have to make to formally meet the definition of a black hole. And you can ask, how close are we with our technology to doing that? And those technologies would be places like national labs, Lawrence Livermore, where lasers are all focused on one area to create enormous compression and density, for example, to cause fusion to occur. or maybe an accelerator like the Large Hadron Collider. But if you look at the math of their ability to create high densities, it's orders of magnitude away from what would be needed to create even a tiny black hole. And by orders of magnitude, I don't mean factors of thousands, I mean factors of billions away. So we're really not close to making a black hole at all.
The next question is from Saeed, who asks, in order for the universe to expand, shouldn't there be a payment for it to expand? So I assume that means that shouldn't there be some kind of energy that is required as payment for this expansion?
Yes, so the energy, there is energy associated with the expansion. I mean, you can think of it as kinetic energy of the expanding objects within the universe and the space-time. And the question of where did that energy come from is, in the conventional theory of the Big Bang, that energy was essentially borrowed from the vacuum of space. So the vacuum of space is not nothing. It contains the potential for energy, and that energy can be borrowed. There's vacuum energy that's measured in physics and has been for decades. And the Big Bang expansion is an extreme version of drawing on that energy of the vacuum to create a bubble of space-time, our expanding universe. And the math of that is worked out in the inflationary model.
The next question is from Dolneth, who's on with us live. What is most likely, which in your view would be the most likely to have life, Titan or Europa?
I think the odds are good that Europa would have some form of microbial life in the oceans, and that's because we have liquid water. It's a very cold environment, but there's energy coming from the interior. There's tidal heating and natural geological heat from radioactive decay in the rock because it's quite a large moon. So there's tepid water at the boundary layer between the floor of the ocean and the ocean water just above. We have inference that there's salty. It's a salty ocean, basically from molecules that were detected by Cassini in the environment of Europa. So Europa really has all the ingredients for life. Titan does not necessarily have all the ingredients for life. It's a very strange chemical environment, and it's not clear you can get biochemistry from the chemical ingredients on Titan.
The next question is from Jerry, who asks, what would you prioritize as the top astronomy-related projects to devote a federal budget to?
Well, it's a tricky question because at the moment the elephant in the room is Mars sample return, which has ballooned to over $11 billion for very expensive samples. I think I did the math and it's $800 million per ounce. So that would not actually be my first choice. Mars samples would be wonderful, but at that cost of $11 billion, you could have so many other missions. I would prioritize another telescope in space. James Webb is a mostly infrared telescope, so we kind of need a successor to the Hubble Space Telescope to work at optical and ultraviolet wavelengths, because a lot of physics happens there and that you can't just see when you're working in the infrared. So I'd prioritize a successor, more direct successor to Hubble than James Webb is. And then I am interested in the life in the solar system issue, and some of the most compelling targets are the targets like Titan and Europa and Enceladus. And those missions are expensive and take a long time, and so they need to be prioritized in a NASA budget.
The next question is from Sphere, who is on with us live. When the JWST detects an object, do we receive information via images, or do we actually get deep spectra of those objects?
James Webb can do both kinds of science. It has cameras that are just making images, and it has spectral capabilities too. When you make a spectrum, though, you're smearing light out as a function of wavelength, and it's got to be detected on top of a background, so there's a signal-to-noise issue. So it's harder to make spectra than to take direct images, and so the depth and the distance you can reach with spectra is less than direct imaging. So James Webb does both, but as far as pushing the limits of space and time, for example, it's always done with the direct imaging capability.
The next question is from Rumana. Can we use neutron stars as gravitational lenses?
Yes, neutron stars have strong enough gravity that they create gravitational lenses. I mean, if you look at the theory of a neutron star and its density, and you imagine doing a ray tracing diagram of a neutron star, the bending of light is sufficient that if we looked at that neutron star, we actually see around the backside. We don't just see the 180 degrees or the front face of it, we see behind it, and that's because of the gravitational lensing. So yes, neutron stars can do gravitational lensing, and we've got indications of that.
The next question is from Sun Eater, who asks, I've been wondering about why NASA decided to put people's names on the moon Europa. How does that work, and why are they deciding to do that?
I mean, NASA looks at opportunities to engage the public and to spread the message and to, gain goodwill amongst the taxpayers who pay the bills. And, the science that's done with NASA otherwise only happens in scientific groups and with people who build missions and spacecraft and with maybe astronauts who go up into space. So the idea of having names on a spacecraft, and there have been a number of names. I mean, the Mars rovers, some of them have had names etched on them. So there have been a number of NASA missions, probably heading towards 8 or 10, that have incorporated people's names. It's easy to do, it's cheap to do, and once you do it digitally or you reduce it to almost a microscopic scale, then it doesn't really cost anything, and so it's sort of a way to create goodwill and public engagement that doesn't really have a downside.
The next question is from Dan Cooper, who asks, and the premise of the question is not entirely accurate, so you can address that as well. Caltech recently had to remove its telescope in Hawaii and move it to Chile. Are all the telescopes on Hawaii being shut down? So I think they mean the 30-meter telescope, unless there's another telescope that was moved from Hawaii that I don't know about. But can you talk about a little bit about telescopes on Hawaii and what's going on with those?
Right. If we're talking about the big telescope, the 30-meter telescope, which is Caltech and the University of California, it is essentially stalled in its construction over issues that are being negotiated with the native Hawaiians. And in that interim, while it's being stalled by several years, they've looked at alternative sites. But the sites they're looking at are not in Chile, actually. The La Palma is their backup site, which is in the Canary Islands in the northern hemisphere. And in fact, there's always been a sense that the 30-meter telescope wanted to be looking at a northern sky, because we already have two huge telescopes under construction, the GMT and the ELT, that are both in Chile. So there's a sense that we don't want all three of the new big telescopes to be in the same hemisphere. It's possible there's a second piece of this, which is Caltech does have a millimeter telescope on Mauna Kea, and I'm not clear about that particular facility, but it's possible that that might at some point be relocated. Because part of the agreement with the native Hawaiians on Mauna Kea is essentially putting a cap on the number of large telescopes on the mountaintop. So if any new telescope, like the 30-meter, is added, then some telescopes will have to be subtracted and moved elsewhere.
Excellent. Thank you very much for clearing that up for me as well. The next question is from one of our online participants who's with us live. Let's see here. Sorry, I lost the question I was going to ask. The question is from Irina, who asks, why did you start studying astronomy, and what made you interested in it for the first time?
I didn't start early the way some people do. There are people who start with a little telescope when they're kids and trade up to bigger telescopes, eventually becoming professionals. I grew up in cities, New York and London basically, and I never had a dark sky, and so I couldn't see stars growing up. I followed a path that many astronomers follow, which is to get into it through physics. So physics is the foundational subject for astronomy, which is essentially astrophysics. It's the projection of physics into the universe. So my undergraduate degree was physics, and then I'd taken astronomy courses as part of that undergraduate degree and thought this is a great subject, and so that's what I picked for graduate school. And I'd say 70 or 80% of the professional astronomers I know did physics as their first degree.
Excellent, thank you. The next question is from one of our live participants. What would happen to Earth's orbit and weather if we lost the moon?
Well, if the moon, I mean, it's an interesting thought experiment. What did that actually mean? If the moon just suddenly disappeared and it's gone and its gravity is gone, then there obviously would be substantial effect on the Earth. This coupling of angular momentum and exchange of energy with the moon would be gone. The Earth's orbit would regularize because it was no longer being pulled by the moon. The tides that the moon causes would suddenly go away, and so the Earth would have no tides, and that would probably be, for someone living on the Earth, the most dramatic change if the moon suddenly stopped existing. I think all the other changes would be subtle and hard to notice.
Excellent. The next question is from an email. How does solar sailing work if photons have zero mass?
Well, photons formally have zero mass because it's electromagnetic radiation, but also in terms of relativity, photons clearly have momentum because when a photon hits something, it transfers energy and momentum. And since energy has an equivalent mass by E equals mc squared, you can calculate or infer an equivalent mass for a photon. So while they don't formally have mass, because things with mass are not supposed to move at the speed of light, then there is energy and momentum attached to photons, and so you can think of in terms of an equivalent mass.
Excellent. The next question is from one of our live participants. Aditya asks, the TRAPPIST system is a bit similar to our solar system and has 3 planets in the habitable zone. How can life thrive in water worlds and planets with extreme temperatures within a thin habitable belt?
We don't know that habitable means inhabited. So habitable is a tricky definitional term because it usually just means a distance from a star such that liquid water could exist on the surface. But habitable also has to do with the atmosphere of the planet, and we don't know what the atmospheres of the TRAPPIST system planets are. And an atmosphere typically warms the planet up if it has any greenhouse gases like methane or carbon dioxide in it, and so that raises the equilibrium temperature. So that information is usually not present for exoplanets. We don't know what their atmospheres are made of. And so we're always pretty uncertain when we talk about the habitability of planets. Also, the width of the habitable zone depends on being sure that water can be liquid on the surface, but water could stay liquid under surface, under a cap of rock and ice by pressure, and that expands the habitable zone again. So the habitable zone is a pretty broad and schematic way to define liquid water's presence, and in the details matter a lot, and so we always need to have more information to calculate properly.
All right, we have to leave a little early today, so the next question will be our final question. We've had 2 people ask about this, and I know it's very hypothetical and theoretical, but it's an interesting way to talk about evidence. People have asked, how do we know that we are not in a black hole? And then somebody else asks, how do we know that the Milky Way and our neighboring galaxies are not in a black hole? How do we know that that shrinking horizon of our universe isn't some kind of event horizon of a black hole, or that we aren't somehow living inside one of these extreme environments?
So a black hole is a very particular object defined by general relativity, and the event horizon of a black hole is also a very particular definition. It relates to a mass density such that light cannot escape, and so there's no escape of particles or radiation or information. There is no real way, by analogy or in terms of physics, that our universe, our observable universe, fits the event horizon definition. There's a horizon, which is an information limit for information reaching us, but it's not the same kind of information limit caused by gravity stopping the information getting out. That would imply incredibly strong gravity beyond our observable universe, and there's no indication of that. So these are evocative ideas, but I basically think that in modern cosmology there's no analogy between our universe and a black hole. Interesting question though, and good range as always. So thank you for participating, and Matthew for facilitating. And I think we have a couple scheduled, so we're back with you in a couple of weeks.
Exactly. Thank you very much. Yes, we will be back on January 17th. So we will see you all in about 2 weeks. Thank you very much for joining us today. We hope you have a great new year, and we will talk to you again soon. Take care, everyone.